Hello everyone. In this talk, I shall discuss our recent work C-MI-GAN, estimation of conditional mutual information using MinMax formulation. Quantifying the dependence between random variables is a quintessential problem in data science. CMI captures the dependence between two random variables x and y given a third random variable z. In its most basic form, CMI is the expected mutual information between two random variables given a third random variable. Alternatively, it can be expressed as the KL divergence between the true joint distribution and the conditionally independent joint distribution of random variables x, y, and z. It can also be expressed as different combinations of the conditional entropy, marginal entropy, and joint entropy terms. Unlike Pearson correlation and partial correlation, CMI is able to capture nonlinear conditional relationship between two variables. CMI finds its usage in feature selection, conditional independence testing, and in causal association detection, to name a few. The traditional methods of estimating CMI first estimate the density using kernel density estimator or k nearest neighbor estimator. Next, they estimate different entropy terms and plug into the entropy based definition of CMI. However, these methods suffer from curse of dimensionality. On the other hand, modern neural CMI estimators are modular in the sense they either use a standalone conditional generator to generate samples from the conditionally independent joint distribution, or they estimate two separate mutual information terms in order to estimate CMI. In this work, we attempt to propose a joint neural framework for CMI estimation. To begin with, we formulate the task of CMI estimation as a min-max optimization problem. We obtain an inf formulation by introducing a variational distribution, which, together with the Donsker-Verdhan bound on KL divergence, provides the desirable min-max objective. We use a generator network to generate samples from the variational distribution and a regression network to parameterize the function class in Donsker-Verdhan identity. We optimize these two networks alternatively. And as we can see, this alternate optimization procedure enables the framework to learn the regression network for a given generator at each iteration and vice versa. And as a result, this method ultimately estimate the true two conditional mutual information of the given dataset. In order to estimate the effectiveness of the proposed method, we consider estimating CMI on different datasets, such as one synthetic linear dataset, one synthetic nonlinear dataset, and real world air quality dataset. We consider three linear data generation models. In the first two models, x and y are unidimensional, whereas the conditioning variable z is multidimensional. As we can see in figure 3a and c, we fix dz and we study the effect of variable sample size. Whereas in figure 3b and 3d, we fix the sample size and study the effect of variable dz. As we can see, performance of C-MI-GAN remains unaffected across all the settings. In model 3, all of x, y, and z are multidimensional, and again as before, C-MI-GAN outperforms the current state of the art CCMI. Next, we consider synthetic datasets with nonlinear dependence. As we can see, on an average, the estimates of C-MI-GAN are more closer to the ground truth and so exhibits less variation as compared to other estimators. Finally, we consider real-world air quality dataset. Here we do not know the true CMI values, and we consider the causal graph as discovered by Runge as the ground truth for extracting different relationships. As we can see, the estimates of C-MI-GAN are in coherence with the findings of other estimators, and also it complies with the ground truth causal graph. Finally, we consider conditional independence testing as an application of CMI estimation. Here we cast the problem as a binary classification problem between conditionally independent class and conditionally dependent class. And we use area under the ROC curve as a metric for comparing the performance. As we can see, the performance of CCMI and C-MI-GAN are comparable for all the synthetic datasets irrespective of the dimension of the conditioning variable Z. However, the performance of CCIT degrades as DZ increases. Next, we consider real-world flow cytometry dataset, and we consider this consensus network for our ground truth. We extract 70 conditionally independent dataset and 54 conditionally dependent datasets. As before, we see the performance of C-MI-GAN is the best. It outperforms both CCIT and CCMI as measured using the AUROC metric. To conclude, in this work, we formulate CMI as a min-max optimization problem. We have proposed a joint training algorithm to optimize the min-max objective for estimating CMI. We have theoretically derived the optimal regression network's expression for a given generator, and we have shown that when the training converges, then we estimate the true CMI value, and also we show the efficacy of our proposed method in estimating CMI on several real-world and synthetic datasets. Also, we show the efficacy of our proposed method on conditional independence testing on synthetic and real-world datasets as measured by AUROC metric. Thank you.